In this video, we're going to look at the third concept associated with these counting techniques. Previously, we've looked at the multiplication technique and we looked at a permutation. We defined what a permutation was, and then there was a formula for the permutation. Now we're going to complete our set of counting techniques by talking about something called a combination. So let's define what a combination is, and then look at the formula, right? So a combination of R elements selected from n distinct elements. And again, even when we just write a phrase or say this phrase, what's implied is that your n is greater than or equal to R, right? Well, a combination of these R elements selected from n elements is a selection in which order does not matter. So in which order does not matter, right? Well, what does that mean? Now, previously, we talked about a permutation. Now, so let's say we have, let's use this as our universal set, A, B, C, D, E. And if we want to permute 3 out of these 5, so 3 of 5 elements, what are some examples of that? Well, one, you might have A, C, D, right? And that's considered a different permutation from this, A, D, C. And it goes back to the concept of whether order matters or not. So in a permutation, if we're using this as our universal set and we're permuting any 3 of these 5 distinct elements, then these are considered different permutations. Now, if we say just select 3 of 5 elements, so just selecting 3 out of 5, then these are considered the same selection. So A, C, D, for example, and A, D, C are the same selection. So again, this is where we don't distinguish between the order, right? And our goal in this video is to come up with a formula for how many of these things can we have versus how many of the permutations, which we already know. Now remember, for permutations, if I wanted to figure out how many of these 3-element permutations I can form out of these 5 distinct elements, then it would be 5. So this would be the formula, 5p3. And, well, this is the notation. The actual formula is 5 factorial over 5 minus 3 factorial. Right? And what we want is we want to be able to come up with a similar formula that will answer the question, if we were just treating them as selections, how many 3-element selections could I form out of these 5 elements? All right, well, let's kind of think about this. So if we have R elements, right, how many ways can we arrange them, right? They may be arranged in So let's see. Let's see if we can figure it out. Well, so think of it this way. We have R slots. Right? So there are of them. Dot dot dot. So here we have R slots, or spaces or boxes, and we have R elements that we are going to arrange in these R slots. So for the first slot, we have R elements to choose from. But after we've placed one of those R elements in the first slot, to fill the second slot, we now have R minus 1 left. And then similarly, after filling the first two slots, and then now we're filling our third slot, well, how many elements do we have left to fill the third? Well, that will be R minus 2, and then dot, 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 until we get to the very last slot. And since we're filling these R slots with R elements, there's only going to be one left over. So how many ways could we come up with this arrangement or this permutation? Well, the multiplication technique tells us that we need to multiply R times R1 times, I'm sorry, not R1, but R minus 1 times R minus 2 all the way down to 1. So if we have R elements, they may be arranged in R times R minus 1 times R minus 2 times dot 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 times 1, and that's just the definition for R factorial. So R factorial ways, right? So if we don't want to distinguish between the different arrangements of these R elements, in other words, if we want, for example, ACD to be counted the same as ADC, well, here's how we can approach this, right? So the N choose, actually, yeah, so let's say this. So let me make one more statement, and we're getting there. So if we select, we've seen this before, if we select R elements or objects from N distinct objects, there are NPR arrangements possible. Right? Again, and these arrangements contains the R objects R factorial times, right? So these arrangements contain the R elements. Let's get this off. So R elements R factorial times, because there are factorial ways that those elements can be arranged. Right? But remember, we don't want to count these R factorial times differently. Essentially, we want all of these times to be treated as one selection of those R objects. So here is the theorem that tells us what to do. So our theorem, and I won't write it formally, but the number of combinations now, which is what we're trying to get to. So the number of combinations of R objects selected not arranged now, just selected, again, from n distinct objects, again, where order doesn't matter, is, now let me introduce the notation. And if you think about it, this notation makes sense. We use P to represent a permutation. We're going to use C to represent a combination. So we're still using N, but what's different now? It's C, R. And it can be written this way. Now, if you've been exposed to the concept of this particular counting technique, you might already know this formula. It's sometimes written like this, and then you have the N there, and then your R there. And the way we kind of read this, we would say like N choose R, right? So again, the selection is just a choice. So this is read N choose R, right? Now what's the formula? Well, if you think about it, when we write this down, we're looking at all the possible arrangements of these R elements out of the N distinct elements. But we just argued up here that there are factorial of these. But we don't want to count all of them individually, right? We don't want to distinguish between ABC and ACB. So what we end up having to do is to divide by how many times that selection shows up, right? So that selection shows up this many times. So we have to have R factorial in our denominator there. And then writing it out, let's see. So remember, the numerator, your NPR is this. It's N factorial over N minus R factorial. But now we're dividing that whole fraction by R factorial. And then the more simplified way to express this fraction is it's N factorial divided by both N minus R factorial and then an R factorial there, right? So this is our formula for the number of combinations, right, of R elements out of N distinct elements, right? Now I will say, when we're making this type of, whether it's a permutation or a combination, it's an arrangement or a selection in which there is no replacement, right? So that's an important concept here. Note the selection or arrangement. So whether you're talking about a permutation or a combination, so in a combination or permutation, there is no replacement of the element. So you don't take one and then put it back, right? So they are done without replacement. And how does that factor in? Well, that, if you think about it, let me scroll back up just for a little bit, right? It factors into our logic right here, that after we fill the first slot with one of R elements, we only have R minus 1 elements left over. So the one that's here, we don't somehow put it back in the pot and it could end up here. So that's why these numbers are decreasing all the way down to 1, right? If you have, in a very basic sense, if you have some kind of selection process where the selection is done with replacement, you have to rely more heavily on the multiplication rule and figure out how many elements are there at each step, right? So just keep that in mind in terms of these formulas are applicable And again, both for the combination and the permutation, these are applicable when you have some kind of choice without replacement. All right, so let's do a couple examples here. So let's look at some examples. And let's start with example 1. So I'm going to kind of, again, summarize, because since these are kind of story problems, I'm going to summarize what's going on and see if we can figure this out. So we have 8 people. So here's a summary. We have 8 people, and what we want to find out, how many 3-person committees can be formed out of the 8. So how many 3-person committees may be formed, right? And again, if you think about the scenario, you have 8 people, and you're essentially choosing 3 out of the 8 to represent the full group. So the order doesn't matter. It's a little bit different from, let's say, choosing a president, a vice president, and a secretary. There, since there are specific roles that are different, then if you were asking, out of 8 people, how many ways could you choose a president, a vice president, and a secretary, that choice implies that the order does matter. But if you're simply choosing a committee of a certain subset, the order doesn't matter, right? So ask yourself this specific question in a scenario like this. Are the individuals going to play well-defined, unique roles, or is it just a subset that will represent the larger group or your universal set? In this case, you're just choosing a 3-person committee. They're not serving any specific roles, and you want to know how many ways can you do that, choosing out of 8 people. So this one is set up exactly for our formula. So the answer is, out of 8, we're now choosing 3, not permuting 3. And then let's write down our formula. So we have 8 factorial over 8 minus 3 factorial. And then at the bottom we have, again, 3 factorial. So this ends up being, now let me just show you simple ways that you can use the definition of the factorial to help you simplify what's going on, right? You don't always have to rely on the calculator. You don't always have to start entering things that could possibly be entered erroneously and then lead to an incorrect answer. So what I'm going to write is this. 8 factorial can be represented like this. It would be 8 times 7 times 6, and then 5 times 4 times 3 times 2 times 1. But that last bit that I said, the 5 times 4 times 3 times 2 times 1, that is 5 factorial. So I can put 5 factorial there. So essentially I can factor the numerator into this factorization, and then I'm going to have a 5 factorial there and then a 3 factorial there. Well, why am I choosing to keep the 5 factorial together? Because now I have a factor of 5 factorial in the numerator and in the denominator. So that factor reduces with that factor. Furthermore, it just worked out in this case that the 3 factorial is exactly 6, right? So the numerator, I have 8 times 7 times 6. In the denominator, 3 times 2 times 1, that's also 6. So I can either further reduce this. So what am I left with? All I'm left with is 8 times 7, and that's equal to 56. So properties like this with the factorial function, Many of these were maybe introduced in previous courses. You may have remembered using them a lot when you're like your Taylor series or just general series that involves a factorial function. These properties help in simplifying expressions, and they also, so not only in a calculus class, but also in a class that uses these counting techniques. All right, so there are 56 committees that can be formed consisting of 3 people out of a group of 8 people, right? So again, you might not think that many, but in fact there are that many. All right, let's look at another scenario. So this one has a little bit more information. So we have a man that has 6 cows. So we have 6 cows, we have 5 pigs, and we have 8 hens. So we got some farm animals here. So these owned by a farmer. And then a man, so a man wants to buy, right, so wants to buy, how many does he want to buy? Well, he wants to buy 3 cows, so 3 cows, and 2 pigs, only 2 pigs, and then 8 hens, so 8 hens, right? So you have a farmer that owns this many cows, pigs, and hens. Then you have a man that wants to buy this many cows, pigs, and hens. The question is, so here's the question, how many choices does the man have, right? So, so how many choices? And my use of the word choice here is important, right? So how many choices does the man have, right? So again, it doesn't matter if you think of it as cows, like C1, C2, C3 through C6. It doesn't matter if he gets them in this order, C2, C3, C5, or C5, C3, C2. It's the same choice or selection of cows, right? Same thing with the pigs, same thing with the hens. So the important thing here in this situation, order does not matter. All right, so that's important. Well, you can think of this, since there are 3 different types of animals that this man wants to buy, you can actually think of those as your A1. So the A1 represents the cows, right? So you can think of this, the A1 represent the cows, A2 represent the pigs, and then A3 represents the hens. Now let's figure out how many choices would this man have as far as cows. Well, he has to choose 3 out of 6. So that's actually, so we have to do a combination to figure out how many cows he can choose. So that would be your 6 choose 3, right? And that particular number, in fact, let me just write down the expressions first here. And then how many pigs? Well, he's choosing 2 out of the 5, so this will be 5 choose 2. And then finally, the number of hens, it's, let's see. Oh, actually, no, he's not buying all 8. Let me change that to, he could, but let's say he wants to buy just 4. So then this would be 8 choose 4. Right? And then let's write down what this is. So we got 6 factorial over 6 minus 3 factorial, and then times 3 factorial. So what happens here? You have 6 factorial over 3 factorial, essentially squared. Well, I'll just write it as times 3 factorial. And then what happens here? You have your 6 times 5 times 4. Just like we did before, we can write that as 3 factorial. And in the bottom, what happens is this. We'll just cancel out everything that cancels out. So the 3 factorial, there it goes. And then the 3 factorial and the 6 also goes. And we're left with 20 ways that this man can choose 3 cows out of 6. Doing a similar process, and what I would invite you to do at this stage is you can sort of pause the video and go through and compute these. And I encourage you, try to do it without, using a calculator. Work those neurons in your brain. But n choose 2 ends up being 10. And then 8 choose 4, a little bit bigger as you might imagine, ends up being 70, right? So these choices that we just computed, this is specifically for cows, this one is specifically for pigs, this one specifically for hens. So in total, this is where we apply our multiplication rule or technique. So applying the multiplication rule, we get that the man has, and remember what the multiplication rule says, you take n1 times n2 times n3, so he has 20 times 10 times 70 total choices to purchase all these, the different numbers of these 3 animals. And when you do your product, you'll get a whopping 14,000 choices. That's a lot. Again, just to buy, 3 out of 6 cows, 2 out of 5 pigs, 4 out of 8 hens, we end up with 14,000 choices, or you could actually use the word combinations, right? And so there you go. So hopefully now that we've looked at all these 3 different counting techniques, I wanted to do one example that utilizes, sometimes you could use all 3, quite frankly, but here we just needed 2 of the 3 techniques. The concept of a combination, and that's when we realize that it doesn't matter how the order in which the man chooses which cows, pigs, and hens he's going to buy. But then, since there are multiple animals being purchased, the total number of ways that he can make his selection or his choice or his combination is by multiplying these 3 numbers. So that's our multiplication technique. So hopefully that helps, and look forward to using these techniques in other sort of bigger problems. And with that, I will see you in the next video.